So we've been talking about rotational motion. We've been talking about the moment of inertia, right? But now it's time to talk about what causes rotation. We know that there has to be some sort of force involved. Force has to be present, right? When trying to make an object spin, I have to apply a force, right? So I would like to do a little demonstration with this. It's just a bar, and we have a way that we can move up and down. And I would like to have a volunteer here hold it in place, like this, right? Can anybody want to try that? You want to? All right, thank you. So hold it there. Not too hard, right? Okay. So you tell me if it feels easier or harder. All right. This is where it was. Let's put it over here. How about that? That's pretty hard, right? Okay, so the force that the effort that he feels is related to how much weight we have here. How much is the weight of this thing, clearly, right? But that's not it, because we had the same weight when it was here, then it was here, then it was here, and yet it felt very different, right? So there has to be an additional variable there that has to do with the ability of a force, in this case the weight, to cause a rotation, right? So another example here, this is supposed to be a door, and you open doors many times a day, okay? So when you try to open a door, of course you have to apply a force, right? I'm going to apply force up here because this is just cardboard. So you apply force. Typically, you apply the force where the handle is, right? I'm going to apply it at different places. If you push here, if you try to open a door by pushing close to the hinges of the door, right, then it's somehow difficult. If you apply a force over here, it's a lot easier, right? So we're talking about the same kind of thing in this demonstration. The force that you're applying has a different ability to cause rotation. Just the magnitude of the force is not enough to tell how easy it is to make an object spin or not, right? You also have to know where that force is applied. So let's do the door here. This is going to be the axis of rotation. And we're going to apply the force. We're going to compare two forces, one applied closer to the axis of rotation, one force acting far away from the center of rotation, right? So one thing that seems clear from your experience is that the force, first of all, is going to be proportional to the torque is going to be proportional to the force, and we're talking about torque as some sort of ability to cause rotation. And the more force you apply, of course, the more torque you're going to have. But it should also depend on how far away from the axis of rotation you're applying the force. In fact, if you apply the force right at the hinges of a door, of course, there is no rotation at all. No rotation at all, right? If you apply it right at the hinges. Because that distance that we're talking about there, the distance between the point where you apply the force, in this case here, or in this case here, the distance between that point and the axis of rotation, if you apply it right at the hinges, is 0. So your torque, since it depends on that radius, on that distance, sorry, then that ability will be 0, right? Now think about what happens. What else might be a factor there? Suppose that I apply the force at this point, the same force every time, right? But in one case I apply the force this way. In one case I apply the force this way. If you want to open the door, that wouldn't be very smart, right? because you can immediately see that that force, even though it might be the same magnitude as the force that you apply this way, this kind of force does not have any ability to cause rotation, right? So what that's telling you is that there's an additional variable that we need to consider when talking about the ability of a force to cause rotation, which is the angle at which you are applying the force. So same door. Let's apply force here. The two cases that we just discussed were a force acting this way or a force acting this way. Let's call this one F1 and this one F2. The torque, the ability of F1 to cause rotation, is definitely different from 0, right? It has some ability to cause rotation. When you apply that force, you get this object, this door, to open, to rotate. But clearly, the torque of force 2 is 0, because that force has no ability to cause rotation. And the only difference between this is that this one is acting perpendicular to the door, and this one is parallel to the door, right? So if you talk about the angle that the vector r, so we're going to talk about the vector r as being the vector that goes from the axis of rotation to the point where you apply the force. Then you can talk about the angle between the force and r, right? In this case, that angle is 90 degrees. In this case, that angle is 180, right? So in general, let's say that if you have a force acting at an angle like this, we'll measure the angle between the vector, between r and the force. And this angle, I'm going to call it theta, is the same as this angle theta over here. Okay. And what we're saying is that we expect the torque to be a function of that angle theta, right? A good function is sine of theta. Because if the angle between the force and the vector r is 90 degrees, then you get maximum torque, right? But if the angle is 180 or if the angle is 0, we get 0 torque. So sine theta seems to do the job pretty well, right? It will give you 0 for the torque when, in this case or that case, it will give you maximum torque when the force is perpendicular to the vector r, right? Notice that that angle theta comes in pretty naturally because we said that the torque of F1, which is, suppose that the force F has two components. F1, which is perpendicular, and F2 is the component that is parallel to R, right? So the torque of the force F, it's going to be equal to the torque of its component that is perpendicular to the vector R, because the other component has 0 torque, right? So the equation for torque, you can write it this way. You can say it's R times F, but not the whole vector F actually produces torque. It's only the perpendicular component of F that produces torque, right? Another way to write that is this. That's where the angle came in. When the angle is 0, F has no component perpendicular to the vector R. When the angle is 90, the component of F that is perpendicular to vector R is maximum, right? It's equal to F. For any angle in between, then that contribution is less than F, correct? Let's write this equation in a slightly different way. Torque of some force F, we say that it's R F sine theta. we group it this way, F with the sine of theta, we know that this is the perpendicular component of the force. Perpendicular to what? Perpendicular to R, to the vector R. So if this is the object that you're talking about, this is the axis of rotation, and the force that you apply is here, applied at that point. Let's say that the force, a little higher, say that you apply a force that way. I'm going to draw a line along the direction in which F is acting. Try to do it as straight as possible here. This is the vector R. And the line along which R is pointing is this dotted line here. So this angle here is what we call theta. Which is the same as this angle theta over here. F has two components. With respect to R, with respect to this line, F has two components. One component that is perpendicular. This is F perpendicular. And a component that is parallel. Do in blue also the force. So what this equation for torque says, the way we've discussed it so far, is that the torque that this force F acting at this point will cause about the axis of rotation, that torque is only due to the perpendicular component of F with respect to R. So this angle is 90 degrees, right? So it's only due to that component. But notice that this equation can be written in a different way. You can write it also as torque equals F R sine theta. Where is R sine theta? It's a distance. Which distance is it? If this is a right angle, over here, if I just draw a line along F, and then I draw a perpendicular line and make sure that that line goes through the axis of rotation, then R is the hypotenuse. I have a right angle triangle here, and this side should be d sine theta. Right? This side should be d cosine theta. Right? From here to there, that's d cosine theta. This is d sine theta. Why am I calling it d? This is r, sorry. R sine theta. And that r sine theta, I'm just going to call it d. Okay, so this is d. D is equal to r sine theta. That's another way to write this equation. I'm just grouping these two, the radius, the distance, and the sine of the angle. And I'm going to call that d. Well, that d has a special name because it's a useful quantity. It has a special name. Otherwise, it wouldn't. It's called moment arm. So another way to look at the torque is to say that the torque caused by a force F is due to the magnitude of the force, right? But the only distance that you're going to count is the perpendicular distance between the line along which the force is acting, which is this line, perpendicular distance between that line and the axis of rotation. Okay? So if you have the same magnitude f acting at this point, and you change the angle at which f is acting, you can see that that d is growing or becoming smaller, and d becomes 0 when the force f is acting along the radius, along the distance. We're calling that radius. That's not a radius. Right? Because then that d turns to 0. Your torque is 0 when the force is acting along this direction. The moment arm is going to be maximum when that force F, you apply it in this direction. Because now the perpendicular distance between the force, the line of the force, and the axis of rotation does coincide with R, with the magnitude of the position vector. Right? So those are, I haven't done anything different. I'm just grouping the terms in a different way and looking at the, expressing that equation in terms of two different quantities. One is the moment arm, d, and the other one is just a component of the force perpendicular to the vector position. Okay? Same equation. Why would you want to have two different equations for torque? It depends on the problem. One of them might be easier than the other. Right? So what I'm saying is that two ways to calculate torque. One is use this. Of course, the basic equation is the same. It's just R F sine theta. But the other way, which might be faster, is F times D, moment arm, right? And the reason for the difference is that in some problems, the moment arm might be evident. It would be just staring at your face, what's the moment arm? So you just have to multiply by F, and you're done with the torque for that force. But in other problems, that's not so evident. You'll have to do some trigonometry to get the moment arm, so you might want to use this. That might be easier. If you have an angle and the distance, for example, that's what you want to use. So let me give you an example of a case where one of them is clearly better than the other one. So suppose you have a bicycle here, bicycle wheel, and you're trying to make this wheel go over step. The height of that step is h. And you're going to do that by applying a force here in that direction. The wheel has a radius r, the step height h, and the force is F. Find the torque of the force F. By what point, you might ask? Torque as moment of inertia needs to be specified with respect to an axis of rotation. What's the axis of rotation? Well, when you pull on this, what you're really trying to do, as I said when I stated the problem, was that I want to make this wheel go over the step, right? When the wheel moves over the step, it's going to be moving about this point, correct? That point where the wheel is touching the step, that's going to be fixed. And the wheel is going to pivot about that point. It's going to go up, right? We're not going to solve the problem completely to figure out how much is the force. I just want to do the first step in this problem, which would be calculate the torque due to F. So which of these two approaches do you want to use? Do you want to use this one, which implies that you know the component of the force that is perpendicular to the vector position? So the force is applied here, so the vector R that we're talking about will be this one. And the angle that we're talking about, the angle between F and R, will be this one. Make that a little stronger. Okay, do we know that angle? Do we know the r, the distance r? We don't, and it looks like you could get it, but it involves some geometry. It doesn't seem very simple, right? So if that seems too complicated, look at the second option that you have. If I use the second version of the same equation for torque, immediately I know what the torque is. How much is it? The equation says that I need to find the perpendicular distance between the line of the force and the axis of rotation. What is that perpendicular distance in this problem? This is the line of the force. I drop a perpendicular line to that. I drop a perpendicular, but it has to hit the axis of rotation. That's not good. That's not good. That's not good. It's got to be this one. Right? That is your D. Is it easy to find D now? Yes? No? Well, in terms of the variables that you have in the problem, D is straightforward. What's the first term? 2r, that's right. And? This is 2r, and this is h. So what's D? When the question is too easy, you're hesitant, right? You're like, can't be that easy. All right, 2r minus h. That's D. There you go. You're done. So something that looked very complicated when you were trying to use this equation is actually quite easy when you use this equation. It doesn't mean that every time this is going to be the easiest way. Sometimes the distance D might be complicated to find it, and you want to go with the other one.